Everybody good with that? Good. Yeah.
I'm not understanding how there's I guess a flow of electrons from one N plus to the other N plus.
Yeah.
I'm not understanding that part. Like, aren't they both, don't they both have like the same amount of like free electrons?
They do, but I'm putting a higher voltage here than here. So now imagine if this was like a piece of conductor, right? So now, imagine if this was a piece of conductor, so I got a resistor. Think of it as a resistor, right? You put a higher voltage on one side of the resistor than the other side, you're going to get current flow. So now it's acting as if it was something like that. Does that make sense? So this has a lot of electrons. This has a lot of electrons. This has a channel with a bunch of electrons, right? And then you're also creating an electric field from here to there. Does that make sense?
Yeah.
What you're asking for, unfortunately, is a very, very complicated, has a very complicated answer. So I hope, I didn't have a plan B for explaining what really happens, but that's the model I'd like you to think about. Okay, go ahead.
Question. So the P is like arsenic, right? And the N would be like boron, right? Or something like that? And because of the lack of...
Yeah, I already forgot what you guys told me, yeah. Just think of it as P-type or N-type for my, what was your quote, sorry, what was your question?
Yeah, I was also confused at how the current would pass through because of that.
Well, remember, what you're doing is you push the voltage on these charges, positive charges that you created there because you put voltage there, have repelled the positive charges, the holes, that were caused, the holes were there. Why were there a lot of holes there? Well, it was because we doped them P, so we created a bunch of holes by the doping of the arsenic or boron, or I forget, right? But you push them away from the surface, okay? Now, you push them away from the surface, there's also electrons there, right? There's just 1,000,000 times less electrons. Any electron that's from anywhere, it sees that those positive charges, they're gonna start coming over here.
So we're just playing around with the proportion of electrons to make sure the current can go by, because there's, I guess in those sections there will be a lot of missing electrons in the negative side, right? And therefore we can actually pass electrons through. Or
Well,
no?
think of it this way.
Sorry.
No. This is the thing is I'm like trying to go too fast here. Let's look back to a time. So this is the same structure, guys. So this is poly. Let's say I put in ground this as well as this. They're both grounded. Okay? So this is without a positive voltage on the gate. All right, so I have positive everywhere. And this is also grounded, and this is on some whatever. Okay? So what does this look like? This looks like two diodes. This is an NP diode. This is N plus P. So this looks like a diode. So I'm going to draw a diode symbol. And this also looks like a diode. Okay? And how are those diodes connected? So remember the diode voltage versus current curve. So this diode, whoops, this guy is going to be right here. There's no voltage across it, that diode. Okay, so there's no current going this way. There's no current flowing here anywhere from this junction into this or any place, right? And this diode has a higher voltage on the N plus than on the P, means that it's kind of here. It also has like no current. This current here, if you got, again, I'm hoping you guys have seen this diode. This is like really tiny current. This reverse bias current. Tiny current. like 10 to the minus 16 amps or something. So basically, you've got two diodes that are off. Okay? When you don't have positive charges on this gate, there's no, you can try to, you can have all the electrons you want here or here. You can have all the electric field you want between them. They're two reverse bias diodes essentially that are not going to conduct current. Okay? Does that make sense? Okay? So how do you, but remember, what we want to do is we want to make, at the highest level, you want to create a situation where you've created a switch that's either on or off. This is kind of what we're trying to build as digital designers. Okay? So now we have an off switch when there's nothing on this gate. Okay? It's a switch that's off. I could have anything on these nodes. This would be the source, sorry, drain, source, gate. Right? The gate turned it off because I got 0 voltage on the gate. And I can have, just like a switch, I can have any voltage I want, drain, source, who cares? The switch is open. You guys with me? So when you put positive charges on the gate, by putting a positive voltage on the gate for an NMOS, okay? Now you've created this channel. You pushed it, you push the positive charges away, attracted the negative charges, which creates a channel between source and drain. You with me?
Yes.
Okay? So now you created a closed switch. Now, if you have, you know, a high voltage on the drain compared to the source, you get a current between them. Peter, is this a good intro to, do you get the MOS transistor at this level? Does that make sense? You said you hadn't seen it before, so I'm asking you. Did you say you hadn't seen it before? You don't remember it?
Oh, I'm Paul.
Oh, Paul, I'm sorry, Paul. I'm sorry, Paul. I told the guys in the previous class too, I don't know if it's old age or getting hit too much in the head. I don't remember anything. Sorry, Paul. So Paul, does that make sense?
Yeah, that makes sense.
Thank you. Okay? Yeah.
So that only occurs if you put a voltage source on the gate, a positive voltage source, right?
Yeah. Like if you put a negative voltage on the gate, what would happen? You would get plus, it would attract holes,
And it'd still be open?
still be open. Now it does something else, so that's called, there's actually something called that is a operating condition for a MOS transistor. It's called accumulation. Okay? Which means you're accumulating holes in your channel. Okay? When you put enough positive voltages here to repel the plus charges, but before you have that electron channel formed here, you call that depletion, because you're depleting that area from positive charges. Okay? So accumulation, if you have negative here, you accumulate holes here. You put a little bit of positive charge, you push the holes away. It's called depletion, because you're depleting this area of holes. And then even more positive voltage, then you have your electron channel. It's called inversion, because you've inverted, you've gone from a hole situation to an electron situation. You've inverted your polarity. In this surface, you went from a positive polarity surface to a negative polarity surface. So you've inverted that. So this is actually the verbiage people use. So if you look at the slides, this is what it looks like, the stages of a MOS transistor, if you get into detail. Accumulation, depletion, inversion, and inversion is when you are on. Okay? Everybody with me? By the way, this whole thing is like pretty damn quick. Like you turn it on, you're talking about like picoseconds or something from like 0 voltage, and then you put it on, pushing these guys away and accumulation you happen, you're talking about 10 to the, I don't even know what it is, it's 10 to the minus 12 seconds or something like that. That's why these things run so fast, right? If this process took forever, like I'm describing it here, so it just goes, right? We put the positive voltages there, it turns on. Okay, now you can think of it as a switch. You guys with me? Okay, so now PMOS, come back all the way here. Was it Jonathan? Did that answer why? I don't know why they call it NMOS, but it needs the P to work. Did that answer why you needed the P channel for it to work?
I think my question was something different.
Okay. Was it still?
So,
Well, go ahead.
so like, we use P-type silicon to make N-type, or P-type, transistors. Why don't we use N-type silicon to make, N-type transistors rather than doping
Yeah.
P-type with one?
Right. Because you're building CMOS, you got to pick your poison. Okay? So what John is saying is, you know what? I could have started with an N-type substrate and put a P well here, and these guys would be sitting on the substrate. I wouldn't need an N well. You with me? Okay, so I think where that comes from, and this is, by the way, it's like pretty much like universal. Sometimes you get what used to be, still have, sometimes you get what's called twin tub, means you would have both P well and N well, just so you can even tune things even more. Now, why is it? I have my own theory of why it is, but I don't know if it's really true. So it turns out that, as we'll see, N MOSFETs are faster than P MOSFETs. Okay? By a factor of 2 or 3, it's got to do with the fact that the electrons move faster than the holes. Okay? So we'll look at that. So N MOSFETs are near and dear to everybody's heart. And the P MOSFETs are kind of like, whatever, we'll get what we get, kind of thing. That's my feeling. So, the less you mess with this, okay, because imagine if I was gonna put a P well here, what would I do? I would sort of, just be more implants, more stuff. There might be a better answer for it, but this is like pretty much universal now. Yeah.
Could you also say that it's just more efficient in terms of like, because the P well, right, has a lot of holes, right? That's what's going on.
People would have.
Because of the electromagnetic field, it would definitely pull down way better than an N well would be able to do it, right?
Well, theoretically, you could just make this a P well.
Yeah.
And like as far as this guy's concerned, theoretically, it just really looks like it's just got P in its channel, so I wouldn't really notice, theoretically. So, but I don't have a good answer, honestly. Yeah.
What's a P well and N well? Like I heard that.
Sorry?
What's a P well and an N well?
Okay. It's a good entree. Thank you that was a leading question. What's your name, by the way?
Alex.
Alex. Thank you, Alex. Sorry, guys. By week 15, I might get your names right.
Day 15, I think.
Huh?
We only have 15 days.
That's true. That's good. Good point. Make it look better. Okay, so remember we've got a CMOS process, so we need PMOS transistors as well as NMOS. I just told you guys how we can get an NMOS. How do we get a PMOS? Well, sort of like PMOS works the same way except in reverse. So imagine if I had an N-type material with a lot of extra electrons. Okay, and then I had my gate oxide.
and then I had my gate. I would have to put in, so what would happen then? I would need to put in negative charges here on my gate to repel these electrons and make this positive. You with me? So it's exactly like the NMOS, it's reverse. Alex, does that make sense?
Yeah, so far.
Okay. So now what I did is I repelled these guys. I got my positive, sort of, my inverted channel is not positive. Okay? But now to get a switch here, I need my source and drain. Well, what type of material do I have to put in for a source and a drain for holes? I need to put in P plus layers, because that's what I get holes from my channel. Okay? Now, as John pointed out, I already made a decision that my substrate was P-well. Whoever made this decision, right? So my silicon material is P-type. So to create this device, this PMOS material, I gotta put in an N-well so that dude can live in it. So my PMOS can live inside this silicon dioxide. This is the gate. So this N-well, I'm trying to create locally, I'm trying to build this device. My substrate was already P, so I'm just kind of screwed. I got to make a mini thing here. So that's an N-well. Why is it called well? Sorry, it's two L's. Why is it called a well? I'm not sure, historic reasons, right?
So if you want a PMOS and a P-type silicon, you need an N-well,
You need an N-well.
and vice versa for.
Vice versa, yes.
Normally when we start so say that we have a wafer, right?
Mhm.
And then we beam that wafer with like you said most of the time they're like N-wells, right? No, they're P-wells?
Well, it just depends on what you make. But normally you would do N-wells on a P-type material.
And then you would just convert that N-well into a P-well?
No, you would just put P-wells here. Let's say if you were gonna make a P-well, you would put P-type P-well here. So what I think what Jonathan is saying is like, and it is possible, this used to be more, I've seen it a few times in my life, but you could easily imagine a situation where you had N-type, and you put a P-well here, and because of this, you wouldn't need an N-well. So the PMOS now would sit in the substrate, and you'd have to have
Oh,
a well for the NMOS. But you don't really see that case much at all. I don't like hardly ever see it. Again, I used to see it in some processes. I really honestly don't know why it went away. Whoops, P, no, wait a minute. So let me just go back. I confused myself. P, and well. Yeah, John, do you have a question?
Is it, cause I know that, like, we don't use typically gallium for making, or is it germanium? One of those.
Yeah.
We typically don't use that to make semiconductors, but would the type that produces be an N-type? And is that why we don't?
Can you say that again?
I know there's like another material that we could use to make semiconductors. I can't remember if it's gallium or germanium.
Yeah, the very first transistors were germanium.
Right.
So you
And
probably think of germanium.
is it possible that those types were N-types? And
It's possible. It's possible. Even silicon though has. By the way, there's a bit of magic. So it happens. My brother happens to be in the same. My older brother happens to be in the same business. He works for Qualcomm's chip designer. So he's a lot less optimistic than I am about mankind. So he thinks this whole process was an accident because nobody has tried, people have tried over the years to create volume semiconductors off of other material, germanium, gallium arsenide,
indium gallium arsenide, gallium nitride is the latest one. Nobody's that successful. Hardly at all successful. And this is the reason, in my humble opinion, this is the reason they tell you in grad school. It's not just the silicon. So why didn't germanium succeed? The first transistors were actually germanium. Okay? Why didn't they succeed? Why did silicon dioxide succeed? I cannot tell you, especially in the 80s and 90s, so much work went into gallium arsenide because their mobility of gallium arsenide, the velocity of electron holes is much higher in gallium arsenide than is in silicon. So the idea is we're going to get really freaking fast transistors. Okay? The reason it didn't work is because not just of silicon, but silicon dioxide. Okay? Because look at this transistor. This oxide layer plays an absolutely critical role here. I'm going to just sort of draw it as an afterthought. But it's the silicon dioxide system that gives you the ability to make these transistors. Okay? And this is a really clean system. You can grow silicon dioxide without a lot of voids, with a lot of defects, which means you can make these really thin. I mean, like I'm just throwing out, we're like simulating with a 40 nanometer process, nobody cares, right? But imagine 40 nanometers is how wide the transistor is. The thickness of that gate, okay? Imagine you're talking about, I mean, I don't know if it's 20 atoms of silicon dioxide or 30 atoms. But we're not talking about 30,000 atoms of silicon dioxide. So the purity of this oxide that you build for your gate, it has to be incredibly pure. And imagine again, 20 billion transistor, one of them has a short on the gate, your device is toast, right? So the level of purity, the silicon dioxide has to be extremely pure. So this is the real reason why silicon 1 as a material is the silicon dioxide system, okay? Does that make sense? That you can grow silicon dioxide easily and in a very, very, very pure way. Purity is not even a word to describe any of this stuff because, you know, if you think about the purity of the silicon wafer, the purity of the oxide, compared to anything else humans make, okay? Or nature makes pure this and pure that, it's so much better than anything you could imagine because you just think about the numbers, right? You've got very few atoms of anything here. You got high electric fields because everything's so small. And you got a ton of them and you're building them day and night and nothing can go wrong with jillions of them. Okay, so anyway, silicon dioxide is why silicon 1 as a material. Okay. So everybody's now, we got our NMOS, we got our PMOS. Everybody's good with that? Okay. This is like, I cannot do anything. This was all to talk to you guys about why this was not allowed, okay? Can't do anything in a short amount. Because everything, you go down the rabbit hole, and the way I'm teaching this class, I got to just accept that I got to drill down where it's important, okay? So bear with my teaching style. Okay, so now I've cleverly, now you got to say, okay, well, so by the way, you guys see how this is a planar process, right? Because now I got this surface, I might have an NMOS transistor here, there might be another NMOS transistor next to him, PMOS, maybe there's an NMOS here, but they're all sitting in the same plane of I can't put an NMOS transistor up above this guy, okay? The connection between the transistor, the metal, we have metal connections, we'll get into that. That's in a stack, but all the transistors are in the plane, in the same planar process. So all the NMOS transistors are in the same substrate, in other words. There is no other substrate. They're all connected in this P material. Okay? So at some point, I need to make a connection to this P-type material. Okay, remember, I said I grounded this p-type material, but how the heck do I ground it, right? You guys can see where I can connect to the source and the drain. So I need to put a P plus here, so I can put my ground, so I can ground the substrate. You guys with me? Because I needed the substrate grounded, otherwise just be floating if I don't connect it. If I have P plus on P, that's just the short. Okay? P plus onto P is the same material. Okay, the reason I make it a P plus is because I'm going to put aluminum or something there. I want a good contact between, so I can put an excess amount of P plus. But P plus to P is just a short. There's no reverse bias side, nothing. So if I put a voltage on this P plus, it's the same voltage on this P. Okay? Yeah, you look confused. Okay. So I had to put that connection there to get this guy, okay, to get this thing to work. So, and I can put a bunch of these P pluses, and you do. You put them all over the surface of your, whatever there's a spare place. I can put a P plus here, and I ground that. And I put a P plus here, ground that. All these guys are shorted together, shorted to ground, and shorted to the substrate. Okay? This means that if I have N transistors, all their substrates are grounded. Okay? I cannot have a situation where I have another N-type transistor and hook up its substrate to something else. It's just not, it's not something I can build in this process. You know what I'm saying? If I took this P plus and connected it to plus 5 volts, I would get a short between plus 5 volts and this ground. I cannot do that, right? They've got to be all shorted together and all grounded. So does this make sense to you guys why this is not allowed? Okay, so you can only have the NMOS transistors going to ground. The sources can be in different places. Like, for example, the source of this bottom one is connected to ground, and the source of this one is connected to the drain of that one. That's allowed because this guy is an N plus connection into the P substrate. Okay? So it's not going to short if I put this to some other voltage. If I put this at plus 5 volts, it's not going to short to the substrate. Remember, this is a junction. It's a diode here. Okay? If I had, this guy was inverted, it would be a short this way, but it's always a reverse bias diode to the substrate. Okay? And same with this one. Meaning that this is allowed. Okay, I can have some voltage on my drain and source different than my substrate or ground connection. But the substrate NMOS connection is always connected to the substrate. With me? Okay. Now, let's say, so that was why don't do this, because you really cannot physically do it in a chip. You could do it if you had discrete devices, right? If you went and bought, that's why SPICE allows you to do it. If you went and got an NMOS transistor in a package and another NMOS transistor in another package, they're not sitting in the same substrate. You could put them in your printed circuit board. You can do whatever you want to the substrate connection. So SPICE is happy to let you do that, except in our world, in the chip design world, you can't do it. Okay? Now let's look at the P MOSFETs. So, where was it? So by the way, you make this connection to your N well, you drop an N plus here, inside your well. Okay? And I can connect this up to VDD. That's how it's done. Okay, so a couple of things. One is, theoretically, if you had two P MOSFETs, theoretically you could put this one in, even in a chip design process, you could do that. Why? Because you could put them in different wells. The NMOS, you have no choice, there's no wells. They're all sitting on the same substrate. But you could put this guy in a different well than that guy and connect them up differently. You see where I'm going with that? Like you could have a situation where you have P plus, P plus, P plus, P plus. Oops. So this is one PMOS, this is the other PMOS. So these are the well connections. So because in my process the PMOSFETs are in wells, I can electrically put different biases on those wells. I can. Okay, it's not like I cannot, that there'll be a short. Okay, in fact, sometimes in analog design we do this, sometimes. But you pretty much don't see it used in digital design at all, but it's possible to do it. The reason you don't do it in digital design is it's physically large, right? So what would happen if they had the same, if they had the same connection, I could stick them in the same well and physically get these two much closer to each other. I'm sort of cheating here with drawing it like this, but because there's rules that says if you have separate wells, they have to be separate by a certain distance. So it's making your circuit bigger. So if I draw it like this, is physically on your chip much bigger than this. Because this one I can put them in the same well. Okay, this one I need separate well contacts, takes up a room. Remember, room, space, equals to dollars lost, right? Because that's how your chips gets more expensive. So you never want to do that if you can help it. Okay, so here, separate wells. There's some rules governing the spacing between the wells. There are different potentials. And then I need to drop in different connections for each one, just more space. So this is much tighter, smaller area than this one. So you also never see this, almost never, I want to say never, see this in a digital circuit. You might see this in an analog circuit for some reasons, because analog isn't as dense as digital and stuff, and we just don't care about cost. We like to overcharge our customers. That's okay. You with me so far? Okay. Now, one more question is, let's say you had just a PMOS. Why couldn't you hook it up like that? You could, right? Like physically you could. Physically, I can connect this guy to this guy. I can connect my substrate to this guy as opposed to up here. Okay? But there's a problem with that. So if I have a connection like this, my substrate's voltage is going to change as my output goes up and down. You guys see that? Because when my substrate's connected to here, it's always at that voltage. It's always at VDD, whatever VDD is, right? It's stable. So all I care about is my gate voltage. If I So in this scenarios that I played with you guys, showed you for you guys, right? I'm controlling this transistor only with the gate voltage because my substrate's at a known voltage. It's either shorted grounded in the case of NMOS, or goes to VDD in the case of PMOS. So I just have this gate connection. So I got this switch model, right? Whatever the gate does, I can turn on and off this transistor. But if I connected up like this, now I've got two terminals to worry about, right? I have my gate, but then my substrate's also going up and down depending on my output. I've just shorted it to my output. And remember, sometimes your output's at ground, sometimes at VDD. So that's also modulating your channel, which is not something you want for a switch. You don't want two separate connections doing God knows what, dependent on some other signal. You want a gate that's controlling that switch, and that's the only thing that's controlling the switch. Okay? So I want to take it all back to all this complexity that I talked about. I've been talking for the last, hour and a half. Okay? If I could, I would shut up and give you guys this. I'd magically created, and you'd have a switch, right? But we have all this stuff that that's what we have, is this really funky transistors where you have substrate connections and, electrons and holes, and I don't want to hear about the holes, right? The hole doesn't even exist. I had to make it up to explain this to you guys. And electrode constant. In the end, this is what we want. Remember, this class is where the rubber meets the road between math, binary logic, binary math, okay, and physics. Okay, this is what you want for your binary math. Ones and zeros, switches that turn on and off. Physics is giving you electrons and holes and silicon dioxide layers and voltages and stuff. So we're just twisting the physics to give us this. But the rest of this class, or all of this class, is about all the second order, all the problems that gives us, all the stuff that we have to watch out for. Well, it gives you this, but you can use it like that, or you can't use it like that, and this switch is worse than that switch. You see where I'm going? That's all I'm explaining to you in this class, all these things, or what physics gives you that you can use as that to do your binary math. Okay? Let's take a little break, 15-minute break. Back here at 2:45. Thanks, guys.